We found these large interconnected networks to be most interesting, mainly with the large porous cavities that were created between them, and these fluid networks seemed ideal to be trapping objects within them. So our theory was, we started off with a solution of vesicles in solution, and this, in our case, we added mixed up some cells in there as well. If we added some PEO, could we aggregate this together, trapping the cells inside, and in effect use it as a way to transport cells around and keep them alive, and then have the gel break down at a later point and release the cells exactly where you wanted them. So we set up our experiment with our vesicles and cells, mixed up, added PEO, and we never imagined we would trap all the cells, but what we were hoping is when these aggregates formed in the solution, we get this large gel network forming, that we would, in fact, trap some of the cells within the gel. And so we made a series of these, and once they were formed, so mixed them up, added the PEO, left them for a day for the gel to form and separate in solution. And then we took off the gel and did an assay to measure the viability of any cells in that. If there weren't any cells, then we would see nothing. And we also measured the rest of the solution separately, so we could see then if we were trapping any cells in our gels, and also how many we were then trapping within the gel relative to the solution.
Would the cells actually sink, or is that just the
so the cells, when you close cells, this is representative of a well plate that you would culture cells in. They like to stick to a surface, so generally they do sink to the bottom and adhere to that surface and watch them grow. So then, also when you're growing them, they do really like to stick to the surface, and you have to add reagents to actually get them to release from the surface, so you can go about and do further experiments with it. So then, based on that experiment, what this shows is the viability of the cells. It all revolves around 1 being 100%. So this was normalized to cells growing normally without any gel or PEO added to them. So they all starting after 24 hours when we make the first measurement. So that's a start. So that's the kind of base start. And then if we have no cells in the gel at all, this wouldn't have shown up anything and would be 0. And then a decrease over time would indicate that the cells didn't like being in the gel. We had them, but they were dying in effect while they were in that. An increase would be cells naturally dividing in solution, and we're getting more and more cells. Or what we saw, which was what we saw on the plate surface, which is what you'd expect, because that's usually how you're culturing them, sitting on the cell and they divide nicely. But then the cells that we took when we took off the gel from the solution didn't really change over time. There was no growth, but no death either. They just kind of sat there. And so further work is currently being done. This is work I did at Sheffield, and this is being further looked into at the minute. So it could be that they're sitting there quite happily, but they're just not not growing in solution. Because, as I said, they like to attach to something. And as we've got, as I said, the vesicles have that layer that stops them coming into each other. That's also going to stop a cell attaching to that surface. So they're not really going to like it too much in there. So that could be why they're not dividing, but it could also be that they're sort of dying within there. But not dying, they could be stressed as well. So there's another test that's being done at the minute to determine whether they're actually happy to sit there or whether they're stressed, and it will eventually lead to cell death if we took this to a longer time period. This is one of the ways in Sheffield that we were using polymers as a delivery system. But at the minute now I've moved over here to Delaware, what we're working on is a polymer that forms micelles in solution. This is the name of the polymer we're using. This is polybutadiene ethylene oxide. This is the structure of the butadiene unit. This is insoluble in water, and the ethylene oxide. So this is this fraction would be the same as the polyethylene oxide that we were using before. And this is the water soluble part. And with these ratios, so this 57 represents there are 57 repeat units of this butadiene unit, and then 187 ethylene oxide units in this polymer chain. And this is just a micrograph taken on the microscope, actually in this building, just downstairs. And the dark circles are in fact the core of the micelle, which shows up nicely. However, there's so much water in the shell of the micelle that it looks, when you're looking down the microscope, it looks pretty much the same as the rest of the solvent in solution. So that's why we're just seeing the dark spots rather than anything else.
Maybe I missed it, but how are you synthesizing these precisely? As in 57 to 187? Just curious.
It's
What did I ask a bad question?
It's so anionic polymerization is the name for it, and so you start off with an initiator in the solution, which is highly reactive and which kicks everything going. And so you have everything dissolved in solution, and you add your initiator, and that kicks it going, and so that reacts with one butadiene unit, which then connects to the next one and the next one, and it goes on. And so you add a precise amount of your initiator, and then you add a precise amount of your monomer units, and so each one of the initiators, a chain grows from that until you run out of the butadiene units. And so everything is more or less the same length. And so that sits in nicely. And then you can add the next one, and then the chains grow on from that. And by the ratio between the initiator that you use and the monomer units you use, you can control then how long each block is. Yeah, in fact, in this one you can see kind of a slightly darker grey ring around it, but as I mentioned, it doesn't show up very well. And so this is current work at the minute. So far we've synthesized the polymer and characterized them. They do in fact form the micelles in solution. And working with